Hello, folks. Today I want to talk a little bit more about moment of inertia. So I'm going to start by reviewing what we've already said about moment of inertia, which is very little. So if you're coming to this new and fresh and you haven't seen anything about it, that's fine, because I'm going to review everything you need to know. Let's see if that black looks like it's not showing up too well. Let me try this color. Oh, that's better. Torque equals I alpha. So all we know about this is that it's called moment of inertia, which is a weird name, not really a very catchy name. This has to do with an old math term that I don't think is particularly interesting for our purposes. And the units are kilogram meters squared. So that's basically all we know about this object, or about this quantity, I should say. And I want to go into it a little bit more, talk a little bit more about why this unit makes at least some sense, and then talk a little bit more about the moment of inertia of a point mass. So we're going towards a formula to understand the moment of inertia of a point mass. But first, let's just start with this. So right here, I have a meter stick. And I have binder clipped 200-gram masses. Doesn't matter what their mass is, but I've binder clipped 2 masses here. And I'm going to hold this in the middle, and I'm going to try and spin it back and forth, like as fast as I can, back and forth. So I don't know if that even how well that shows up on the video, but I'm basically going back and forth as fast as I can. And I can go back and forth really fast. In fact, maybe you can even hear the air I'm moving around by moving that meter stick around. Okay, so that's meter stick number 1. It has the meter stick itself, of course, has some mass, but a lot of the mass is actually concentrated right here in the middle. Probably 4/5 of the mass is around here. Now, hopefully I don't break a meter stick. I have the same kind of meter stick, same 100-gram masses. So this meter stick has the same mass as this one. Okay? This one has the masses in the middle. This one has the same masses, but they're clipped at the ends. And now I'm going to try and spin this around. You can see it's sagging already. I'm going to try and spin this around back and forth without having the masses fly off. And even if I try to spin it fast, I am really trying, actually. I would say, whoa, that's about, I'm trying about as hard as this is the meter stick where the one is in the middle. Like, this is even easier. Like, I can do this all day. This one, just going back and forth like this, is really hard. So what that tells me is that there's more to the story than just the mass itself. Okay? There's more to the story than just the mass itself. So, 1 second. Okay, so what we need to think about, and what I'm going to do, is I'm going to break this down into the simplest possible thing and analyze that. So instead of having it balanced like this, I'm going to imagine taking one of these off. I'm taking one of these off, so now there's only a mass here. And I'm going to pretend that this meter stick is massless. I'm going to spin it around this end. Now, I really almost can't. But I want you to have the visual of a massless rod with a mass at the end, and I'm trying to spin it. And that's what we're going to do some derivation work with. So we're going to do some formulas and to look at that scenario. Because that scenario actually turns out to be nice and simple to analyze. Relatively. Simpler than some of the other crazy things that you can spin. So here I have a mass. At the end, here I have the pivot, right? And I'm going to call this length capital L. Okay. So what I'm going to do, so I'm also going to work, this is a little hard to show you in the video, but I'm not going to work like this, where my hand is exerting a torque to spin it and gravity is fighting it. I'm not going to do that. I'm going to go even simpler. So I'm going to imagine that this is on a flat table. It's kind of coming out towards you, and I'm spinning it like this. Can you see that? That's kind of like coming towards or coming away from you. And it's supported. So there's like a frictionless table here. So the normal force is up, gravity's down, and they cancel out. And I'm spinning it so that it comes around in a circle. Okay? So in the plane of this picture, gravity might be going in and normal force would be going out, and I'm ignoring them both. They're both going to cancel here. And so I'm going to exert a force, some force F, and I want to think about how this object's going to move. So this is going to go around in a circle, sort of dot, 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 come around like this. It's going to go around in a circular path. And if this is a frictionless table, this thing is going to speed up and speed up and speed up. If I'm going to keep pushing it, so I'm going to kind of keep exerting a force no matter where it is. If it's come around, so it's spun around to this point, I'm exerting my force like that. If it's at this point, I'm exerting my force like that. So I'm just kind of keeping up with it, pushing with my finger, and it's going to go faster and faster and faster and faster and faster. Okay, so do we have the visual for that? So the question in my mind is, let me frame this as a specific goal. Okay, so my goal is to determine, whoops, that's not how you spell determine the angular acceleration in terms of force, because it's clearly going to matter how hard I'm pushing it. I'm going to push it, and it's going to speed up in a circle. We know speeding up in a circle is angular acceleration. That's what this alpha is, aka fish. So in terms of force, the mass is presumably going to matter, because if it were more massive, it would be harder to get spinning. And the length of this rod might matter too. Okay, so my goal is to determine alpha in terms of F, M, and L. So let's do that. So I'm going to write down that F net for this object equals MA. Now, that's true. The rod is exerting forces sort of in and out, and I'm going to, like, the object is going to do its acceleration in a line tangent to the circle. So and I'm going to continue to push tangent to the circle. So what that means is this F net, I can choose to write it as just my F. My F is the only thing that matters. I sort of concocted this whole scenario so that would be true. So again, remember, like, the normal force, you can't really see like, you can kind of see my finger. The normal force maybe points into the board and gravity points out of the board, or the other way around. In any case, gravity and normal cancel here. All we've got left is this F. Okay, so I'm going to choose to not call that F net. I'm just going to call that my F. And then I've got my mass, so I'm already in good shape. And my goal was to determine alpha. So alpha and A are related to each other. So I'm just going to put a little sidebar over here, and I'm going to write recall. With the definition of the radian, we have S equals R delta theta. That's arc length equals the radius of a circle times the angle measured. V equals R omega. Omega is angular velocity. V is regular velocity. Meters per second for V, radians per second for omega. And then A equals R alpha. Okay, well, I can just rearrange this bottom one. Actually, I don't need to rearrange it at all. I'm just going to plug in R alpha over here. So I'm going to write this as M R alpha. Except let's go back and look. So this was in our little recall sidebar thing that we first talked about a little bit with, what am I trying to say? Angular kinematics, rotational kinematics. We talked a little bit about this stuff. Hold on just a sec. So we talked about that a little bit with rotational kinematics. We haven't used it a ton, but we do use it a little bit. Keep in mind, these are generic. This R is like the radius of the circle we're going around in. So let's come back out of this, like, these generic equations to our specific setup. In our specific setup, the radius is just L. Like, I've given it a different name than R. It really doesn't matter. But I'm going to write this R as L, because that's the size of the circle that this is going to go around in. Right? This is going around in a radius R. I mean radius L, I should say. Okay, so we're almost done. In fact, maybe we kind of are done. This is great. My goal was to determine alpha in terms of F, M, and L, and now here I have F over L equals M alpha. Okay, nice. No, I'm not done though. And the reason I'm not done is that I would really like to rewrite my goal. So new goal. The old goal was good, but here's my new goal. Relate torque to alpha. Okay, you might see where we're going because I just erased torque equals I alpha. This is how we're going to come up with our definition for I. Okay, so we would like, so let's just remember, so we're at this stage, we have F over L, but that's not torque. I'd like to rewrite this in terms of torque. So let's write down our torque formula. Torque equals RF sine theta, where theta is the angle between R and F. Now in this case, the angle here, if this is perpendicular, I decided I was going to push perpendicularly the whole way. So I don't need my sine theta, because sine 90 is 1. And again, this R, this is the generic version of the formula, but my radius here is actually L. L. Okay. So it looks like I can rewrite this as F equals torque over L, and then plug in over here. So I'm going to do that. So I'm basically copying this equation up here over L equals M alpha. But I'm going to write torque over L here. So torque, and then that makes about an L squared. So here I'm going to actually get my second goal, which was to relate torque to alpha, and I get ML squared alpha. Okay. This is actually kind of a big deal. I spent, I don't know, some period of time saying, well, I is just a thing, it's just a proportionality constant. You'll be given to it as a number. But it turns out that for a point mass, which is what we have here, we call it a point mass because the mass is all located at one spot, right? We didn't say, well, it went from this edge to that edge. We're just like, the mass is concentrated here. It's a distance L away. So for a point mass, where should I write this? I think I should fit it here. For a point mass, I equals ML squared. That's actually kind of a big deal. We just calculated a moment of inertia. Right? We just calculated a moment of inertia for this object. In fact, it's the only one we're going to directly calculate. The rest require calculus. But it gives you a sense for where this comes from. So this ML squared comes from starting with F equals MA, and then sort of converting our A into alpha, converting our F into torque, and then writing it in this form, torque equals I alpha, where the I is ML squared. Okay. So what we found here, is that, again, I'll just write down torque equals I alpha. Great. But we found through our calculations that I, for a point mass, equals ML squared. And it turns out that we can kind of make a lot of sense out of that. So if we go back to this scenario, if we think of the meter stick as not having very much mass, and most of the mass, we'll treat the mass as all being concentrated at this point. Then, if I make my L just the distance from my hand to the point mass, again, we're kind of ignoring this part, that's pretty easy to spin, right? And as I make the L bigger, it gets harder and harder. Ooh, I may break the meter stick if I keep doing this. Harder and harder to spin. You have to watch to the end of the video and hit like to figure out whether my meter stick breaks. Don't actually do that. I mean, do watch the end of the video. But this gets harder and harder to spin. And in fact, if you go twice as far away from the mass, it doesn't get twice as hard to spin. It gets 2 squared. It gets 4 times as hard to spin. So if I'm holding this at 50 and I'm trying to spin it, I'm like, all right, that's kind of hard to spin. And if I hold it at 100, it's way harder. Noticeably, I mean, I'm really close to breaking this meter stick, really noticeably much harder to spin. And it turns out that, that all moments of inertia I'm back. All moments of inertia have this feature of, I'm just going to say I anything. Depending on the shape, it'll have a different fraction or some number up front. It might be a half, it might be 2/3, 4/5. There's all kinds of various numbers you can get here depending on the shape. But the moment of inertia of any object, even if it's a weird shape, is something, some fraction, times the mass times some kind of length squared. Sometimes it's written as L, sometimes it's written as R. So if you go and look up formulas for moments of inertia, you'll see a bunch of ML squareds and a bunch of MR squareds. I'll just leave it as L because that's what we used for the mass. But I will write or some number times mr squared. And I use a capital R because it's the size of the object. So when I say I anything, what I mean is it could be a sphere, okay? It could be a donut, right? You can calculate the moment of inertia for a torus, which is the mathematical name for a donut shape. You can, if it's spun about like this, if this is spun about its axis there, a wheel, so something that has some thickness, and sometimes it's a sum of terms. So this is like supposed to be visualizing a wheel being spun about like that. Sometimes it's a sum of like ml1 squared plus ml2 squared or something like that, but it always has the same structure. And the big thing I want you to notice is how important L is. When L is squared, that means that if you have some mass that's far away from the axis of rotation, it's hard to spin. Much harder than just linearly hard. So what I mean is, like, if I'm holding this and I'm trying to spin around the axis of my axis of rotation, the axis, this is the distance. If I double that distance, it's 4 times as hard to spin. And so you can start, if you think about it, you can start making connections with things like anything where the human body is spinning. So whether it's a jump and a spin in dance or in figure skating, Olympic high diving where people tuck into these, a ball and then they expand out again. Anything where you see something spinning and changing shape from compact to extended, all those things have dramatic changes in their moments of inertia when some of the mass gets far away from the axis. And that actually explains quite a lot about rotational motion for things that are changing shape.